Hello and welcome to the class on section 5.2, logarithms and exponential models. We have a quiz today. It's on classes 4, 5, and 6. That's this material right here. Also, you should be working on project 2, which is due next class. So take a look at the date that is right after, or that is in this row. Project 2 will be collected next time, and then project 3 will also be assigned next time. One other thing, our first required forum is due by midnight of whatever the next class is. Lots of details about the required forum are up on Moodle, so go find them and see if you can submit a good forum post. Okay, here we are in the class notes. I say project 3 is assigned, sort of. It isn't, not until next time we're here, but if you finish project 2 early, you might want to get a jump start on project 3. Today we tackle a bunch of word problems that involve exponential and/or logarithmic equations. Our first task is to be able to convert between a of t equals a e to the kt and a of t equals a times b to the t. Those are basically our two exponential growth formulas. The first one, the one on the left, is the continuous model, and the one on the right is our standard annual growth model. For each function, find the continuous and effective annual percent growth rates. And then there are two formulas. So let's make sure we're clear on the lingo. The continuous annual percent growth rate is K. It's easy. It's whatever number is sitting up there. The effective annual percentage growth rate, well, it's called R, and it's the R in this formula. So if we wanted to, I guess we could solve this thing for R and say that R is really B minus 1. So if you happen to know B, B is given to you in the problem, just subtract 1. That's R, and that's the effective annual percent growth rate. So there are two problems here, A and B, and we're asked to find two rates for both. So that's four things. Now, two of them are going to be easy, and the other two we have to do work for. Let's get the easy ones out of the way. A or B, which one is the one that's going to be easy for us to find the continuous annual percent growth rate? Well, it's the one that is in this form, and it's the number that is K. It's right there. So we'll write this, let's write this in purple. So the continuous growth rate here is negative 0.05 or negative 5%. And then which one is it easy to find the effective annual percent growth rate? Well, it's the one that has the B in it, because whatever the B is, you just subtract 1 and that gets you the R, which is what we're after here. So in this problem, 1,000 times B to the T. So there's my B. So we just got to subtract 1 from it. I'll write it down below. The effective annual percent growth rate. So I'll leave a blank space. We got work to do in the first example, but in the second example, it's just R. No, we don't need to put a letter. It's just 1.065 minus 1. 0.065 or 6.5%. Okay, so let's now do the tougher parts. So we'll start with A. The tougher part is this effective annual percent growth rate. Okay, so the goal is not to have it look like 12e to the negative 0.05t, but rather have it look like a times b to the t. Because then if we know b, we just subtract 1 and we get our r. Well, let's clean this up, because right away we know what a is. It's just 12. So essentially the 12s cancel, right? If I want to solve this thing for b, I can divide both sides by 12. And in fact, we didn't even really need to write them, but we'll put them and then get rid of them. So now I'm looking to make these two things the same. And then what else cancels? Well, the t's cancel. It's actually not super easy to see exactly what to do mathematically to make them cancel. You might think about that. But the t's do go away if you do the right thing to both sides of this equation. So ultimately, we're left with this, e to the minus 0.05t, nope, t is gone, equals b. Super. B is the thing we were after. Now it's just a calculator problem. So e to the minus 0.05, put it here in red, that's going to be the b. And then just like we did over here, we took the b and subtracted 1. So we're going to subtract 1 from this thing. So let's type this on the calculator. E to the negative 0.05. We'll just leave it as it is first. Okay, 0.95, that's the B. So this problem right here is really equivalent to 12 times 0.95 to the T. And then if we want the actual rate, we subtract 1, we get something negative, about negative 4.88. So that's the effective annual percentage growth rate. And now we'll do the hard work for the second problem. We're trying to find the continuous growth rate. So I would really like for this formula here, 1,000 times 1.065, to look like the continuous formula, AE to the KT. If we could just get our hands on K, we win. That's the end of the ball game here. Okay, right away we know what A is, so let's put in A as 1,000. I'm just going to copy that E to the KT that we had here. And it's kind of silly because the thousands just cancel. We didn't really even need them in the first place. And now that we have that equation, what also cancels? Well, it's the t's. Again, you got to think about exactly what you should do mathematically to get rid of those t's, but there is something that you can do to both sides to get rid of the t's. And we get this, trying to find k to solve this equation. All right, where is k? Where's the variable? It's up in the power, which means we're using logs. 1.065 equals e to the k. I'm going to put log in front of both sides. I'm going to make a choice. I'm going to pick ln because this problem involves e. And when we do that, the ln and the e cancel. And so then we just get k is equal to ln of 1.065. And that's something we can type into the calculator. And our continuous rate, a little less than the 6.5%. I think that should make sense if you think about it. So about 6.3%. So there's our final answer to that problem. Okay, moving on to number 2. For any kind of exponential growth model, what does the phrase doubling time mean? Okay, so doubling time has to do with how long it takes for something to double. So we can just write that. Perhaps we can just write that. Three. Suppose the formula A of t equals 1,000, 1.06 to the t, models a bank balance. How long will it take for the money to double? Okay, and then quadruple. All right, so let's see. How much money do we start with in this formula? Well, we know that the principal is the number sitting in front. So we start with $1,000. So if I want it to double, then how much money do I want to have at the end? Well, we want to have $2,000. So 2,000 equals that thing. Solving for t, well, the variable is in the power. I feel like we're going to use logs, but first we have to get that exponential piece by itself. So we'll divide both sides by 1,000. 2 equals 1.06 to the t. Next thing to do is take the log of both sides now that the variable exponential part is by itself. So let's go ahead and take ln of both sides. I'll recopy my equation, but leave a little bit of space in between. So we left the space in there so that we could put ln in the space. I'll go ahead and use regular log here. It doesn't matter whether you use log or ln. And then the nice property here on the right-hand side, so I'll copy log 2, but the nice property here is that the power can come down in the front. That t can move right down into the front of the log, making it accessible. And so we take both sides, divide by log of 1.06, and we get t. So we'll type this into the calculator, get our approximation for how long it's going to take for our money to double. So a little under 12 years. We'll say 11.896. Okay, part B says in this case we want our money to quadruple. So instead of starting with 2,000, we would start with 4,000. That's the goal. Still have 1,000 at the beginning, but we want it to grow to 4,000. Okay, let's do a few steps at once here. We'll divide by 1,000. We'll get 4. We're going to take the log of both sides. Log of that. The t is going to come down. Log of this. That was a bunch of steps in one, so do that more slowly if you need to see the details. And then divide both sides by the log of 1.06. So we get log 4 over log 1.06. Exactly the same thing as we had here, just it's now a 4 instead of a 2. Okay, so doubling has a 2 up there, quadrupling has a 4 up there. I think there's a pattern that we can believe. Let's find the quadrupling time here. So it's the same thing we just had, but log 4. 23.791. Okay. So did you notice anything about the relationship between the two answers to these problems? It takes just about 12 years to double, and then just about 24 years to double the second time. So I don't know here. What if we subtract these two answers? Or what if we divide the two answers? Let's store this one here as A. And then I'm going to do second entry to get the previous answer back up here. We'll do this 3 times. There's that one. And then we'll divide that by A and just see what we get. Ooh, 0.5, exactly 0.5. The quadrupling time is exactly double the doubling time. And that kind of makes sense because it took 11.896 years to double the first time, but then once it's there, it seems like it's taking another 11.896 years to double again. So it makes no difference how much money you start with, how much you want to end with. If you're doing 6% interest, it takes 11.896 years to double. Number 4, the rule of 72 is a simple formula that allows you to approximate doubling time. If R is the growth rate as a percentage, not as a decimal, then doubling time is approximately equal to 72 divided by R. Okay, T is roughly 72 divided by R. So, and it says sometimes the rule is used with a 70 instead of a 72. So let's use the rule. How long will it take for money to double according to that formula? Well, wait a minute, that's this formula. So we already know what the right answer is. The right answer is 11.896, and it required quite a bit of work to get there, but we got there. Let's use this much simpler looking formula for the doubling time. So it says it's 72 divided by R, approximately, where R is the interest rate. So 72 divided by the interest rate here, it's a 1.06 in the parentheses. So the interest rate, remember, B is 1 more than the interest rate. So subtract 1 to get 0.06. But this is actually the only time where we don't write the interest rate as a decimal, but rather we just write it as if it were a percentage, even though we don't write the percent symbol. Plain old 6. It says it here in parentheses as a percentage, not as a decimal. It's very, very rare to do that. But if we divide 72 by 6, we get 12. 12 years is the approximate doubling time. How good of an estimate is it? Well, the right answer was 11.896. 12 is a very good estimate, especially given how easy it was to get. 72 divided by R. It's a nice little rule of thumb, very, very accurate. Sometimes folks use a 70. If you did 70 divided by 6, it wouldn't be that different. Let's see what we get there. 70 divided 6. 11 point, it would underestimate a little bit, but still be very, very close to this 11.896. Number 6, this question is from RJ McDaniel. Fill in the blank with the word always or sometimes or never and discuss with a neighbor. For a given interest rate, the doubling time in years of an exponential growth will blank, always, sometimes, or never, be greater than the value of the interest rate. So I don't know if you have neighbors nearby you right now that would be willing to discuss this, but discuss or contemplate on your own, pause the video and come back when you think you've got something. Okay, how about we just start fiddling around with some numbers. I'm going to make a little chart here where I have R as the interest rate, T is the doubling time. So we've already seen that if the interest rate is 6%, then the doubling time is roughly 12 years. So in this case, which one is bigger? So the doubling time is bigger here. What if we made the interest rate smaller? What if we went to 2%? Remember, T is roughly 72 divide R. So if we take 72 divided by 2 at 2%, we get 36 years. So which one is bigger? Still, the doubling time is bigger. Can we get it to go the other direction? Well, let's see. What if we tried 10% interest rate? 72 divided by 10 is 7.2. Which one is bigger now? Now it's the interest rate that's bigger. So what's the conclusion here? For a given interest rate, the doubling time in years will sometimes be greater, sometimes smaller. Wonder if you could find a place where the interest rate and the doubling time were exactly the same. Number 7, what is half-life? Half-life is kind of like doubling time. Half-life is how long it takes for a substance to be cut in half. That's not a very good way to say it. How about we add here for a quantity of a substance to be cut in half? How long will it take for half of the stuff that's there to disappear? So you could ask this question about money. If you had your money in a losing investment where you lost money every year, how long would it take to become half? Maybe more realistic, if you have a certain salary but you're spending more than you're earning, your money will eventually disappear in your savings account. So you can ask questions about half-life there. Also very common is to use half-life when we're thinking about carbon dating. Number 8, carbon-14 has an annual percent decay rate of 0.0121%. What is its half-life? So carbon dating is really important. It's given us a very good sense of how old things were when they were really, really old. Carbon is particularly useful because it has a tiny, tiny, tiny decay rate. So living creatures have a certain amount of carbon-14 in them. When the living creature passes away, the carbon-14 slowly dissipates, but it dissipates really slowly because that right there represents less than, let's see, so it's only about 1/100th of a percent that disappears every year. So that means it takes a long, long time for this carbon to disappear in any significant amount, which means that when we find the bone or the fossil or the tree or whatever, thousands, hundreds of thousands, millions of years later, it might still have some of the original carbon in it that it had when it was alive. And by measuring what percentage we have there, it actually has to do with, oh, I don't remember all the chemistry or biology about it, but I think it has to do with the carbon-14 not just like going away in the breeze, but being converted into something else, maybe an isotope. I'm not sure if that's the right word. But in any event, we can measure what percent of the carbon-14 is still there. And that's very useful to us. So let's find the half-life here. Says that there's an annual percent decay rate of that. Okay, so we'll use our A times B to the T. And in this case, it doesn't really matter what A is. I'll just call it 1. Imagine we have one stuff of carbon-14, and the percent decay rate is a 0.0121%. So that means that the R is 0.000121 as a decimal, and it's a decay, so it's really negative. And we know that the B is always one more than the R. So that means that the B is 1 plus that number right there. Now, I'll trust myself to do arithmetic at this stage in the game, so let's just type that in. So we go 1 plus negative 0.123121. Okay, 0.999879. I should have been able to do that. 879. So that's the B. Very, very slowly decaying. So 1 times 0.999879 raised to the t power, and we want a half-life, we want to know the half-life, so we want to know how long it takes for the stuff to get cut in half. So we started with 1 stuff. That was a choice that I made here. So we eventually want half of that amount, so we want half of the stuff. So just half. So this is the equation that we're trying to solve. I'll write it without the 1. 999879 to the t is supposed to equal half. Okay, how do we solve for the variable when it's in the power? We use logs. I'll use a common log here. You could just as well use a natural log. And then we get to take that power and move it down to the front, making it accessible. And then finally divide both sides by log of that 0.9 number. So we get our answer. Log half, divide, log 0.999879. And we can type that into the calculator. And this is going to give us the number of years it takes for the amount of carbon-14 in this fossil to be cut in half. 5,728 years. That's a long half-life. That's why we still have a chance to tell we can still find carbon-14 in this object, even though it's been dead for thousands or hundreds of thousands or millions of years.